Howdy, everybody. Just want to give one more code review for another day, day 22. I think this is the last code review I'll do. And then I did want to implement day 25 in Rust, so I feel like I have like a quote unquote 25 days in Rust or whatever. And maybe some other videos, I'll try other languages and stuff like that. But these are the last two videos, I think, for this advent of code, unless you all have something that you would like me to talk about, right? So I'm going to talk about a new implementation for solving day 22 today, and then we'll have an upcoming video where I actually implement the Steuer Wagner for day 25, just so you can see how that looks in Rust. And then that will be like all I have for advent of code. So after that, we can do other advents of code if you want. Maybe there's some other days that will be interesting. I know there's some solutions that I've done in the past just recently, where it was, I used a star to solve it, and so that might be a cool one to look at. There'll be things that we can anyway. There's lots of things for us to look at after this, but those are the last two videos I have to talk about, at least for the year 2023. Again, unless there's something specifically that you'd like to talk about a day in 2023. So let me know what those are if you have any. Otherwise, let's get on with the changes. So day 22, maybe I can just recap what it's about. It's sand slabs, and it was a Tetris-y style thing, or Jenga, I guess. The idea is you're given these like blocks, and they're like the Tetris 1x4 white blocks, right? But it's in 3 dimensions, right? And you're gonna get blocks that are of different lengths, but they're all like a 1 by X. And they're either going to be this way, or this way, right? And so your first job is to take all the blocks and drop them down so they all land on top of each other, fall on top of each other. And then for part 1, it's asking you, are there any of the blocks that are safe to remove? And the short way to think about that is they're safe to remove if any of the blocks, a block is safe to remove is any of the blocks that it's holding up have some other block that's holding it up as well, right? So I'll show you in a minute, but you can think about any of the above blocks have other blocks below it. That would make it a safe block. And then part 2 is asking a similar question, but almost in the opposite way. It's saying, find all the, I want you to see if you can create like a chain reaction of blocks falling. And what does that mean? Well, if you remove a block, it would cause a chain reaction if the block above it would fall. And then you check that recursively for all the blocks. And what does that mean? Well, for any block, every block above it that it's supporting would fall if it's supported only by that block, meaning that there's no other blocks that are supporting it, right? And my implementation used just a list of blocks. We can look at it really quick as a reminder. I really just kept a list of blocks, and this right here, I just kept a list of blocks. I did drop them. Sorry if you can hear the motorcycle, but there's a list of blocks and I drop them. But once I've dropped them, all the work I do is over that dropped list. So whenever I'm calculating if they're safe to remove, I go through that whole list and I have to check if that list is, can you guys hear the microphone or the motorcycle? Sorry. I usually don't mind it when the neighbor does that, but when it's recording, it's a little weird. So, okay, so how, again, I have like this list of blocks, and the question is that block safe to remove? I have to like go through that whole vector of blocks and check to see which ones are above it and which ones are below it. So the list isn't large, but it's like 12 or 1300 I think the input has. And so you actually have to check like that whole list to find the ones that are above it, and then find the ones that are below it, and so on and so forth. So if you run it, I'll just show you like my initial implementation. Don't peek below, right? But right here, in total, it takes about 2 seconds to run, right? And it's mostly this second part is 2 seconds to run, because you're doing a lot of checking above, checking below, checking above, checking below, and that list is relatively large, and so you're doing it enough that takes quite a bit of time. It's faster if it's optimized. If you like run the optimized, like you actually compile it, you know, it now runs in milliseconds, but it's still relatively slow. Gordon 508 though mentioned, and I think they had done some other stuff in other days too. So again, thank you for all your input, Gordon 508. They mentioned the way that they implemented it was in a graph, and if you think about it, that actually makes a lot of sense. In fact, my solution to the falls faster, right? Like which one falls, it uses a graph-like thing, right? Is like I'm doing a breadth first search, and obviously a breadth first search is intended for a graph. So why I didn't use a graph to begin with, I don't know. Probably just going from part 1 to part 2, didn't think about it a lot. But think about the graph, right? Is like for any node, I want to kind of track who my parents are and who my children are, right? So this node has no children, but this node has this as a child, and this node has this as a child, and this node has this as a child, right? And I won't do them all, but you just so you get an idea of like, you know, the general consensus is the red ones are the children, and the blue ones are like the or the red ones are the belows, and the blue ones are the aboves, right? So having this in a graph style structure, it needs to be directed, right? Because you want to know, is it above or is it below? But once you have this, it's fairly easy to reason about it, right? Like, if we ask the question, is this bottom block safe to remove? It would be like, are all of its aboves supported by some other block? And in this case, that's not, right? Because this neither of these have any belows, and so it's not safe to remove. You can answer that question though quickly just by consulting your aboves and belows, right? The edges in your graph. You can look at the edges in your graph and say, hey, is this safe to remove or not? And so you can do that much more quickly than like filtering through the whole list of things, right? And then the same thing for part 2 is like what this one would cause these to fall, because these ones have no other children, no other ones below it, right? They have no belows other than this one. And so it wouldn't work. They wouldn't be able to they wouldn't be supported by anything else, and so they would fall, and you can do that recursively. I hope I said that last part correctly. I didn't confuse any of you, but the general idea is this really is a graph if you think about it, and if you treat it like a graph, then you can solve it faster, right? So in other languages, you probably don't have a lot of decision making to do. I mean, there's always multiple ways to define a graph, the data structure of a graph, right? And there's a couple ways to think about it. And in other languages, it probably doesn't matter how you do it, but you do have to do a little bit of thinking in Rust. And so that's just the rest of this video. That's kind of what I'd like to talk about, is like how to think about it. What are the 2 ways to think about it, though? Maybe the 2 common data structures of a graph. You'll see a lot of times in like computer science stuff, they'll say like a graph is a set of vertices and a set of edges. And the vertices would be like, you know, each of the blocks, and the edges would be each of these arrows, right? And so it's not uncommon for this to be like a set and this to be like a hash map. of like this one goes here and this one goes here, right? The hash map helps, especially in something like this where it's directed. You want to have like those pointers, right? So you'd have like some kind of hash map tracking them. The other way is to have each of the nodes know about their own things, right? So you imagine you'd have a block and you'd have its, its X, Y, Z stuff within it. But you'd also have a list of belows and its aboves, right? So these as well are going to be a list, right? But it's all tracked within the block. So this block's implementation would say, oh, I'm at whatever, XYZ, but it would say my belows are empty. There's nothing below me. My aboves are this block and this block. So it's let's say this is A, B, and C. For this block right here, its aboves would be A, B, C, right? And that's the way you'd kind of track your aboves and belows. Though there's two ways to do it. I'll actually show you both implementations. In Rust, this one's a little bit tricky, and I don't want to go into too many details. If you want to talk about Rust Borrow Checker, especially like dynamically, we can talk about that in another video. But the idea is you have to use this RC, the reference counter, to track all of the places that our item is being used, and we need to use a ref cell to track where it's being borrowed, and like treat it as a pointer is maybe the way to say it, right? The ref cell acts as a pointer, and the RC acts as like a counter of how many places that pointer is being used. And we just have to do that in Rust for the borrow checker. So you can see there's a blog here that I found too, that talks a little bit about it as a binary tree. We use the same things because, I mean, if you think about it, a binary tree is just a specialized version of a graph, right? You put additional constraints on the graph, and that's what makes it a binary tree. But the thing about the binary tree is you still have these like pointers, right, to other values. And just to maybe, I don't know, belabor the point a little bit more, in C or in Go, you would just use pointers. No one would care. In Rust, you can't, or you don't want to do that, because one of the main advantages of using Rust is, the safety guarantees that it brings you, right? Is it says, oh, I'm not going to let you, borrow things that you shouldn't be borrowing, or once you take ownership of something, I'm not going to let anything else touch that thing, right? And these RCs and ref cells are a way to borrow, but to do it in a way that is like quote unquote safe. So it will check at runtime to make sure you aren't doing anything that would cause problems, right? And so we do have to use these. And so this solution in Rust it's actually not harder, but it takes time to think about. And you have to use those RC ref cells, which I'll show you in a minute, but you have to use those to help solve it, right? So again, these are the two kind of ways to describe a graph, right? Is you have a list of vertices and edges, or nodes and edges, and then or you have like each block is tracking like what its aboves and belows are. So I'll show you the two implementations and maybe the pros and cons really quick. The actual implementation doesn't change. I should say, again, it's just the underlying data structure, right? So the save to remove functions look relatively the same. This is my initial implementation, right? Is I just want to find all my aboves and make sure they have some other thing below them besides myself. The falls faster implementation is, again, a breadth first search. So I'm going to have some frontier that I'm working off of. And I'm going to check, I'm going to add myself to the frontier and to the fallen list. And then I'm going to check and say, hey, would any of the blocks above me fall? And they would fall if they have no other blocks below them, right? And then I'm going to add that to the list. I'm slowly going to traverse the graph until I've gone through, I've gone through all the places I can, and that's the answer to my question, right? Or that turns out to be how many falls for each of those things, right? For each of those. So how do I implement them differently? Again, the very first initial implementation was just a vector where I'm doing a bunch of filtering and checking, finding values in the vector. And that was the one that took a couple seconds to run. So how do we implement it in like this way, the how you'll often see it in like math terminology? Well, I'm actually just going to keep a list of aboves and belows. So these are our like quote unquote directed edges in the graph. And so for each block, I'm going to have a list of blocks that are above it, and I'm going to have a list of blocks that are below it. You could potentially store these in a single thing, right, where you have aboves and belows, but I just stored it in two hash maps, and that seemed to work just fine. I don't know that you gain anything by having them in a single one, really. I suppose if you're severely memory constrained, putting them together might be shorter, but anyway. So what do I do when I'm like, now I need to like build the actual graph? How do I build the graph? Well, I just go through each block. I need to move it like I did in the initial example, right? I need to like find where it goes and put it in its new position, right? So this doesn't change for most of the code. That still is the same as before. But now I need to go through my list of blocks, and I need to find the ones that are directly below it, right? And what are the ones that are directly below it? Well, it's where the z is -1 and it intersects in my xy direction, right? And then for each of those, so now I have a list of ones that are below me. I need to add those to my below list, right? So I'm going to find my block in my below list, and I'm going to extend that list with these right here. And then I also have to do it in the opposite direction, right? So for each of my belows, I'm going to go into my above list and add myself to being above that item, right? So I'm essentially, the way to think about it is I'm doing this, and these red ones are the belows, and these blue ones are the aboves. And this is, sorry if this looks a little ugly. Maybe I could have tried to clean it up a little bit more. But these are just, Rust functional iterative ways of saying, okay, get all the ones that are below me and add them to my below list for myself. And then for each of the below ones, I need to add myself to their above list. So then once I do that now, right, so this is this part right here, I can now relatively easily reason about the two parts, right? So for part one, it's if I'm above, or for each of them, I want to check all of the aboves and make sure they have some other below. And again, sorry, this is just Rust functional stuff. I could have probably done this in a for loop and made it look nicer or something like this, but the idea is for each one above me, I need to check to make sure that it has another one below it. And if it does, then I count it for that part, right? Otherwise, I don't. And this is just syntax for doing that type of work, right? And then how does part two work? I have this false graph function, and as opposed to having like a list of all the blocks, I really this time only need my own block, and I need my list of aboves, and I need my list of belows, right? And the breadth for search doesn't change. The only thing that changes is this part right here, where I'm calculating what are the new blocks that would fall if I'm removed. And again, it looks a lot like what we did in part one. We're just doing the opposite, right? Is we want to find all the blocks that are above me, and for each of them, we want to find out if they have no blocks below them after I remove the ones that have fallen, right? And so that, again, that's what Sorry again if it looks a little weird if you're not familiar with the Rust syntax, or I didn't write this very clearly. But the idea is, again, find all the aboves and only include them if they have no belows other than me, right? And I add them to my frontier. So it might look, maybe I can show you what they kind of look like together. Again, all of this code is the same. Let me shrink it down a little bit. Right, we're still doing a while let sum, all that stuff. We're still adding in them to our contain lists and stuff like that. It's just the question is, how do we find the new fallen blocks? And in this way, again, I'm on this side, I'm iterating through the whole list and trying to find them. Whereas on this side, I can use my pointer, sorry, not my pointers, my two edge hash maps to get those lists and find them, right? So now I'm only consulting the one as opposed to all of them. The one map as opposed to all of them, I guess I should say. So let's run that really quick and I'll just show you what it looks like. You can see the time is substantially faster, right? This is me using the hash maps. 89 milliseconds, 2 seconds, a total of 2.3 seconds or so, right? This one now runs in microseconds, and as opposed to seconds, this one now runs in milliseconds, like a total time of 144. These don't totally add up. This includes the setup time, right? So the same with this one. This includes like the setup time of everything. So the times aren't exactly right, but that does become important in the next part I'll show you in a second. Right? Obviously, you have to set up the graph, and so that takes time. But you can clearly see that this was a great way to solve the problem. And so thanks, Gordon508, for that, that notion of using a graph as opposed to just like iterating through a list and finding the values that I need to find. That clearly helps you, right? So one last way, right? We talked about doing it this way. What if we do it this way right here, right? We say, okay, well, let's treat all of them. And this is, again, where we have to use like these things. I won't talk about them too much again, but we need to use like some borrow checking stuff in Rust to do that. So the way that I did this is I created a new structure called a graph block. It still has a start and end, but now I have my aboves and belows, and it's just a list of the ones that are above me and the list of ones that are below me. And you can see I have to use these. These are like the borrow checkers way of using pointers. You wouldn't have to do this in other languages, but those other languages are potentially not safe. We're not doing anything crazy with this, so I don't know that the Rust borrow checking helps you a ton, but I thought it would be interesting for you to actually see what it looks like implementing it this way, right? So how first of all, we need to build the graph, right? So we need to build all those links to each other. And so how do we do that is we're still going to keep our list of dropped things, but we're going to go through all the blocks. We're going to drop it the same way we did before, except now we're creating a graph block based on that block as opposed to just a regular block. We're going to add ourselves to the list, and then we need to go through all the drop blocks, and we need to find the ones that we need to update, right? So we want to find the ones we need to update. That's where we intersect with them. And notice this is the Rust thing. I have to do these borrows all over the place. And this is me saying, hey, I want to borrow this value temporarily, but then I'll be done with it, and so someone else can use it later on, right? So I'm going to do these borrows temporarily, and then after this function, or after this like closure is done, then I don't need them anymore, so something else can borrow them. And then for each of them, so for any of them that intersect and are just below me, I now need to update my my above and belows, right? And so that's what this code does right here, right? So I need to borrow the block and add me to its above list. Notice I'm doing a borrow mute here. So this is me telling the Rust runtime borrow checker that, hey, I need to borrow this to update it. And then after I'm done with this code block, you can have it back. But I need to add myself to the above list. And then I also, for the block itself, I need to add that block to my below list, right? So I need to do a borrow mute of that as well and add it to the below list. So that's what you do, right? And the way to think about it is, again, up above, when I'm building the list, I'm just updating my aboves and belows in the hash map. Down here, I'm updating the actual values, or the actual like graph blocks with their aboves and belows. Okay, so what does the falls look like for that one? Again, it's not much different. That we're doing a lot of the same stuff. But in my mind, this almost looks a little cleaner than the previous one. Essentially, we're going to just, again, we're finding all the aboves and seeing if they have some other thing below them. And if they don't, we can add them to our list of ones that we're going to drop, right? But you'll see all these borrows here. I have to do a bunch of borrows again because of the Rust stuff. And if we run it, what do we get? It always takes a little bit of time to run it because that first one takes a while, right? It takes 2 seconds. But you can see total 2 seconds. If we do our hash map implementation, it's total 146. If we do our graph, it's 158. If you notice, though, and this is the case, I've ran it several times, the actual like solving part 1 and part 2 are actually faster, right? This is 53 microseconds versus 678, and this is 109 versus 123. That's always the case, right? Is part 1 is always substantially faster, like an order of magnitude faster, and part 2 is always on the order of like, I don't know, 5 or 10% faster. But the total time is always slightly larger by about 5% or so, somewhere in that range, right? Some small percentage longer. And why is that? Why is this one like faster overall, but this one is faster for the parts? It's that graph building time, right? If you think about what I'm doing here is I'm just shoving new values in hash maps, whereas right here I need to go find the vertices and update them as I'm dropping blocks, right? And so it takes a little bit longer. And I hope that's what you'll get out of these two parts, right, in the code, is that if you're solving a problem like Advent to Code, either one's probably fine, right? These are both really fast, substantially faster than this. So again, thanks to Gordon 508 for, this idea, clearly way faster than doing it this way. You definitely want to use a graph. It's just a question of like, how do you want to implement that graph? For Advent to Code, it probably doesn't matter, but it may be something to think about when you're using this stuff in a real world scenario, right? Like maybe you're building out this huge graph, this huge network, and you want to do operations on it. Using the hash map, it may be faster to initially build, but if it's just like a one and done thing, this might be a faster way to do it. Whereas if suppose you're building a graph and you're going to maintain that over a long duration, adding and removing values and then doing new calculations as you add and remove, you can see like this way is faster, and so you may want to implement it that way. Just again with the caveat of Rust, you may have to do some additional magic to make sure the borrow checker doesn't scream at you too much. Or at all, right? Obviously, if the borrow checker screams at you at all, you don't compile. And so you have to use those ref cells and stuff like that. So there you go. That, again, thank you very much, Gordon 508. That is a great thing you pointed out about using a graph. Again, I used a depth first search, so I think it's clearly like a graph structure. And so treating this as a graph would make it easier to like answer those questions. So that's a cool idea. Maybe just think about how you try and solve it in the future, right? If you're doing Advent to Code this way, especially with the borrow checker, and if you're not familiar with it, it may take a little bit of time to implement. but may answer the actual parts faster once you've built the graph. Whereas using hash maps in a more like traditional, like this type of way, how you'd see it in like a math or computer science book, for, I should say, like for the definitions, right? We've looked at them before and they talk about vertexes and edges and nodes and links and stuff like that, right? This way may get you a total time that's a little faster. So, you know, just things to think about, I guess, is what I'm saying for all of this. So there you go. That is the last code review. I don't have any more. That being said, if you guys, if any of you have new ways of doing some of these things and want to point them out, I'll happily check it out and try it. Otherwise, I think the next video I'll try and do the Stoy Wagner implementation for day 25 in Rust, and then we'll move on to other stuff, other previous years of Advent of Code, other algorithms that might be interesting to look at. So I've got lots of things that are on my mind that I'd like to talk about. But as always, this is a community. As you've seen from these 2 days, I'm learning from you all as much as hopefully you're getting some interesting things from me. And so we're all learning and growing together. And I just want to keep doing that. So if you have things that you'd like to show, or some cool things that you're doing that you think fall along the lines of computer science puzzle solving, let me know. I'll be happy to talk about those as well, or just something you want to learn. Otherwise, I'll keep working on the list of things to do. So there you go. Everyone have a great day, and we'll talk to you next time.